Okay, we are treating compound 1 and 2 with TSCO and pyridine to convert our bad leaving group to a good leaving group. And we have a hindered base, potassium terbutoxide, and Zizeb elimination product dominates. And this is very important because it determines which beta proton we have to abstract for the elimination process to happen. And normally when you have a sterically hindered base, we prefer to have, or it favors the Hoffman, but this is gonna be the game changer here. Determine the stereochemical outcome. And then we have to draw the expected product, and Newman projection is important for compound 2. Alright, I'm gonna start with compound 1. Okay, as you see here, if this is a leaving group, we have a 2 beta proton we can have. But before that, let's first convert this to OTS. I'm gonna skip the this kind of reaction because that's not very important for this problem. So we either have the hydrogen here or hydrogen here. Okay, now let's imagine if you cleave off or abstract the hydrogen on the left carbon here to the leaving group alpha carbon. If we do that, we're gonna have only 2 substituents like this, or we can have like that. So it will be very stereo selective, and we can do better than that by forming a double bond on the right side. So we're gonna focus on I drew it wrong. Okay, so we have a hindered base that's coming along. So it's gonna come and grab that hydrogen. So we have this reaction, E2 reaction. Why E2 though? That's because we have a secondary carbon and we have a base, a very sterically hindered base, and it's not gonna favor the substitute SN2 reaction. So besides, even if it's not, it still favors the E2 for the secondary carbon here. Okay, so that gives us the double bond between this. So let's draw that. Oh, before we do that, let's actually make sure, although this is anti-periplanar, we're gonna also have to draw the Newman projection because the question asks us to do so. So let's see, our eye is looking at the carbon-carbon axis here, the bond axis. So here is our eyes, so we're looking at it, and there's a hidden hydrogen on this OTS with a wedge bond, and so that's like sticking out to the right side. The bottom will have this alkane chain with the aromatic ring attached. In our back carbon, okay, we are looking at through this carbon-carbon bond. On the back, we see hydrogen is sticking out to the right, and then there's a carbon that's stretching up here, which is correspond to that that bond, and then there's one that sticks out to the left with the oxygen attached, and then this forms a square, so quadrilateral, so 1 2 3 4, that works. Okay, so this is our Newman projection for the first compound. Now notice that the leaving group here and the hydrogen on the back is gonna be anti-periplanar. So this is good, and we don't have to do much. We just have to eliminate these two and then form the double bond on this front carbon and the back carbon. And then CH2, CH2, and then you have pH. And for this specific case, I'm just gonna actually draw the phenol, or actually not phenol, phenyl group. And on the left vinylic side, I have to have the oxytone ring. Okay, so as you see, we have Zizeb because we have one substituent, two substituent, three substituent. Okay, so that answers part 1. Now let's move to part 2. This time we have a wedged leaving group, and again I'm gonna convert this to Toslake group thanks to the TSCl and pyridine. And again, we have a third butoxide that's going to come along and play the reaction. However, notice that the hydrogen, the implied hydrogen on our beta carbon is not anti-periplanar, but we have a single bond that can actually rotate to favor the reaction. So let's do that first. I'm gonna have our eyes looking at through that carbon-carbon axis again, and also I'm gonna draw for the hydrogen that's in the dash. So when I take a look at this through this specific bond, and our eyes is here, I'm gonna have an OTS on the right side. On the left side, I see the hydrogen sticking out, and the bottom is still same chain that we saw earlier. And on the back carbon, we have to have carbon that's sticking up, and it's gonna form a ring, and the hydrogen should stick out to the right, and there is the oxygen here. It's not periplanar, as you see, the OTS, and the hydrogen is okay, it's over here. Okay, so we can actually rotate through this carbon, and we can achieve that by it's easier to rotate the front side than back carbon. It's just easier to draw. So keep the drawing on the back, and I can rotate this counter clockwise, 120-degree rotation. Again, that's possible because we have a single bond. If we have a double bond, then that's not possible. Therefore, I have OTS on the left side. Hydrogen now is at the bottom, and the long chain is over here. Okay, so notice that they are like 180 degrees apart. So now if I draw this, it's gonna have double bond, okay, so I just drew these two parts correspond to the right side of the vinylic carbon, and on the left side I should have a So on the left side I should have this. Now we have a different isomer here. Over part 1 we had a, how should I say, the oxygen trumps over the carbon here, so therefore we have a oxygen, and the methyl trump over the hydrogen. This is what we call the same side, so it's a zuzamine, Z isomer. However, on the compound 2, notice that it's enkigen, so it's opposite, unlike the same side here. So we have E isomer.